Well, I'm going to speak today about morphic fields. And morphic fields are the organizing fields of self-organizing systems at all levels of complexity. They underlie the organization of minds, of bodies, of crystals, of plants, of molecules, of stars, and of galaxies. They're the fields that give things their form, their shape, their organization. So I'll be talking about the nature of morphic fields. I'll be talking about the way they have a kind of memory within them through morphic resonance. And I'll be talking about various experiments for testing for their existence. But first, I'm going to start with a very brief history of fields, because the whole theme of our gathering is fields. And the field concept is really a concept that's transforming the whole of science. It wasn't there in the 17th century when mechanistic science got going. The machine metaphor that science was based on from the 17th century onwards was mainly clockwork, and that was the metaphor used for trying to understand the cosmos. But things changed a lot in the 1840s, right here in London. Throughout the 18th century, people had been trying to understand electricity and magnetism, to no avail. It was a kind of amateur hobby. Rich gentlemen had electrical and magnetic machines in their houses and gave sort of demonstrations of sparks and electrical attraction and magnetic attraction and repulsion. But no one understood them. Everyone was fascinated by it, but no one understood it. In the 1840s, Michael Faraday, working right here in London, invented the field concept. And he used the English word field, which really means a piece of tilled land, an area with a boundary, already used in English in many different uses: football field, field of interest, field of view, etc. Many normal English uses for this word, all of them meaning a region of activity. An agricultural field, the source of the metaphor, is a region of activity. If you stop cultivating it, it reverts to scrub and finally woodland. It's a region of activity. And he thought that magnets had regions of activity, and so did electrically charged bodies. And he showed that the electrical and magnetic fields interacted. It wasn't until the 1860s that James Clerk Maxwell gave us the equations of electromagnetic field theory and showed that light was an electromagnetic vibration in the electromagnetic field. Now, this then became the basis of electrical technologies and other forms of electromagnetic radiation like X-rays, ultraviolet, infrared, radio waves, none of which were known about before this revolution. It was a completely revolutionary insight into the nature of nature. But what were these fields? Everyone asked Faraday that question, and the answer was he didn't know. He had two theories about the fields. One was that he thought the fields might be fundamental to all nature. Fields are invisible structures in space. In fact, he thought that they may be, as he put it, modifications of mere space. His alternative theory, his less favored theory, was that fields are made of subtle matter, the ether. Well, the 19th century was rather materialistic. Maxwell took up the ether version of Faraday's theory, and all 19th century electromagnetic theory from then on was based on the ether, an invisible form of subtle matter pervading all space. In 1905, Einstein, in his theory of relativity, what Faraday, his idea that they were just modifications of space, in a way, that's what Einstein went back to. In his special theory of relativity, he showed that ether doesn't exist. We don't need the ether. He just got rid of it. The fields are fields. And so people said, what are they made of? He said, they're not made of anything. Fields are fundamental in nature. Matter arises from fields, not fields from matter. Fields are not made of matter, rather matter's made of fields, of energy bound within fields. In his general theory of relativity in 1927, Einstein showed that the universal gravitational field is a field. It's what holds the whole universe together. There's a field that links everything in the universe together. And so that was another kind of field, different from electromagnetic fields. In quantum theory, they came up with quantum matter fields. Electrons and protons and all other particles are vibrations in quantum fields. So what's going on? What is the nature of these fields? Well, the string theory, superstring theory, is an attempt to tie them all together in terms of a grand unified field. But there's another kind of field which physics has so far not recognized, and that's what I call the morphic field. The fields that organize the forms and shapes of self-organizing systems. And those are the fields I'm going to talk about now. Well, here's a magnetic field, and the point to realize here is that the field is not just within the magnet, it's all around it. It's outside the boundaries of the material object. Fields are more extensive than material objects. And this is why the philosopher of science, Sir Karl Popper, said that through modern physics, materialism has transcended itself because its fundamental explanatory entity is not matter, but fields and energy. Matter is less fundamental than fields and energy. And since materialism is based on the doctrine, the most fundamental thing is matter, this is no longer true. And here you see the pattern in space around the magnet revealed by iron filings. If you took the iron filings away, the field would still be there. The invisible structure would still be there. Now, in the 1920s, biologists working on the development of fungi, plants, and animals came up with a biological field concept. Nobody understood then, and they still don't understand today, how embryos develop, how a complex organism like ourselves arises from a fertilized egg with very little structure. And the idea was that developing organisms are shaped by form-shaping fields, morphogenetic fields. Morphogenesis means the coming into being of form. Morphe means form. Genesis means coming into being. Morphogenesis is the way that animals and plants, all living organisms, or even crystals, have forms that come into being. They weren't there before. After a formative process, they are there now. More structure comes from less. The idea was that this process was guided and shaped by morphogenetic fields, fields that shape the forms of living organisms. They're like invisible plans or blueprints. The reason we need this is that DNA and chemicals alone can't explain morphogenesis. All biologists agree on this. Molecular biology has made it even clearer that this is the case. Think of your arms and legs. They have different shapes, and yet they have exactly the same genes. In fact, all the cells of your body have the same genes, the same so-called genetic program. Yet they're all different. Your eyes, your spleen, your liver, your kidneys, they're all different. And your arms and legs are different. The arms and legs have the same chemicals. Chemically, they're identical. Yet they have different shapes. Why? Well, you can't explain it in terms of chemistry or DNA. You need a kind of plan, an architectural plan, and that's what the morphogenetic field provides. It's a bit like an architectural plan of a building. You could build two houses completely different in shape out of the same building materials, bricks, cement, timber, etc. The difference between the two houses is not in the matter they're made of, nor in the amount of energy involved in building them. It could be the same for both houses. It's the plan that underlies them. And that's what these fields do. They provide the order, the structure, the plan, or if you like, the information, where information means that which puts form into something, information. That's what the fields are doing. Here's another example of an electromagnetic field revealing that the sun has an electromagnetic field that stretches out throughout the entire solar system. The Earth has a magnetic field. When they interact, this is called the magnetopause around the Earth. As a tail stretches out for many millions of miles into space, and it's constantly vibrating and oscillating. This field nature of the universe is what we're only in the 20th century and the 21st century coming to realize. In the 19th century, and certainly at the time of Newton, the universe was seen just in terms of the bare bones of matter, gravitation was what was the obsession of all astronomers. But this has, as it were, put the flesh on the bare bones of the gravitational view of the universe, showing the field nature of everything, of the Earth itself. Now, when we come to embryos, this is an embryo of a bat. All of this develops from a fertilized egg, which has very little structure to start with. How do all these different limbs, these structures come into being? What tells the cells what to do? The answer that within biology is now a very mainstream answer is the morphogenetic fields of the bat. That's what shapes it. There's a kind of invisible shaping blueprint. Here you see a series of stages in the development of a nematode worm, a humble worm, with only a few thousand cells. It starts with an egg cell that divides in two, and then you see it going through a series of stages until this consists of many, many, many different cells with all different structures within it. These fields that shape developing organisms are different. Each organism has its own kind of field. And one reason why biologists liked and still like the idea of morphogenetic fields is because fields are intrinsically holistic. You can't take a slice out of the Earth's gravitational field. You can't take a slice out of magnetic field. If you try and cut the North Pole off a magnet, you just chop the North Pole end off a magnet, you don't end up with an isolated North Pole. You end up with two magnets, each with a complete magnetic field. Now, this is the very nature of fields. They're holistic, they interconnect, they give form, structure, pattern, and connect things together in a whole. If you cut magnets into little pieces, you get lots of little magnets, each with a complete field. Now, that's totally different from the way machines work. Machines are made of parts put together artificially in factories that work together in the entire machine, but it doesn't have an overall organizing field that makes it a whole. If you cut a machine up, a computer up into small pieces, all you get is a broken computer. So field phenomena are very different. And living organisms are much more like field phenomena than like machines. If you cut up a machine, you just get a broken machine. But if you cut up or damage an embryo, that's not what happens. Here you see a normal dragonfly embryo inside the dragonfly egg. In this one, the egg was tied off and this part was killed. The back half of the egg would, in a normal case, have just given the back half of the embryo. But in fact, this part of the egg now has a complete but small embryo within it. So by damaging this, this now has a complete morphogenetic field, like half a magnet. It has a complete magnetic field, and it leads to a normal embryo forming. No machine would do that kind of thing. We see the same with regeneration. If you cut a plant up into lots of little bits, each cutting can become a whole new plant. Willow trees are particularly good at forming cuttings, and you can make thousands of cuttings from a willow tree. This is a flatworm that, cut up into 3 bits here, each of the bits can regenerate. The tail bit regenerates a new middle part and head. The middle bit gets a new head and tail. If you cut it crosswise, you get a new worm. If you cut it in half, from top to bottom, it regenerates a new half. Each of these fragments has the field of the complete worm associated with it, just like a fragment of a magnet has a complete field, which leads to this regenerative healing process. These are limbs of a newt, and in this case the newt's arm was amputated at this point here. On this side it was amputated at this point, much further down. In both cases, the stump regenerates a whole new leg. And again, this is best understood in terms of the field which remains associated with the limb, even though the limb has been cut off. Now, we have much less regenerative capacity than newts. You cut off a person's arm, it doesn't regenerate. We do, of course, regenerate in many of our tissues, the skin, the intestinal lining, the liver. We do have considerable regenerative powers. Without them, we wouldn't heal after damage. But less than a newt. However, I think even human beings, after losing limbs, still have the field of the missing limb, and I think that's what underlies the 17th century when mechanistic science got going. The machine metaphor that science was based on from the 17th century onwards was mainly clockwork, and that was the metaphor used for trying to understand the cosmos. But things changed a lot in the 1840s, right here in London. Stars and of galaxies. They're the fields that give things their form, their shape, their organization. So I'll be talking about the nature of morphic fields. I'll be talking about the way they have a kind of memory within them through morphic resonance. And I'll be talking about various experiments for testing for their existence. But first, I'm going to start with a very brief history of fields, because the whole theme of our gathering is fields. And the field concept is really a concept that's transforming the whole of science. It wasn't there in the 70s. Well, I'm going to speak today about morphic fields. And morphic fields are the organizing fields of self-organizing systems at all levels of complexity. They underlie the organization of minds, of bodies, of crystals, of plants, of molecules, of... Throughout the 18th century, people had been trying to understand electricity and magnetism, to no avail. It was a kind of amateur hobby. Rich gentlemen had electrical and magnetic machines in their houses and gave sort of demonstrations of sparks and